Welcome back. Today we're going to explore one of Rust's most elegant design decisions. We're talking about copy types. When does Rust make copies instead of moves? Let's find out. Before we dive in, let's quickly remind ourselves of what we learned about move semantics. When we create a string and assign it to a new variable, ownership moves to that new variable. The original variable becomes invalid. This is Rust's default behavior, and it's what keeps memory safe. But here's where things get interesting. Not all types behave this way. Watch what happens when we work with a simple integer. We create a variable x with the value 5, then assign x to a new variable y. And here's the surprising part, both x and y are still valid. We can use both of them. The value wasn't moved, it was copied. This seems to break the rules we just learned, but there's a good reason for this behavior. Let's visualize what's actually happening in memory to understand why these two scenarios are different. On the left, we have our string. The variable s1 sits on the stack, but it points to heap-allocated data containing the actual string. When we try to assign s1 to s2, ownership of that heap data moves. The old variable becomes invalid, and only the new variable can access the data. On the right, we have our integer. The variable x contains the value 5 directly on the stack. When we assign x to y, Rust simply copies that value into a new stack location. Both variables now have their own independent copy of the number 5. No pointers, no heap data, no complications. This is the fundamental difference. Simple types that live entirely on the stack can be safely copied. Complex types that manage heap data must be moved. This behavior isn't random. Rust has a formal system for this. Types that implement something called the copy trait are automatically copied instead of moved when assigned to a new variable. It's that simple. If a type has copy, you get a copy. If it doesn't, you get a move. So which types implement copy? Let's look at the usual suspects. All the integer types, your signed and unsigned integers of various sizes, whether it's U32, I64, or usize, they all implement copy. Booleans, a simple true or false value, is copied. Floating point numbers, both F32 and F64, are copy types. And characters. The char type represents a single Unicode scalar value, and it's copied. There's one more interesting case. Tuples of copy types also implement copy. So a tuple of two integers is a copy type. But here's the catch. If any element of the tuple is not copy, like a string, then the entire tuple cannot be copy. One non-copy type ruins it for everyone. Why this distinction? Why can't everything just be copy? It comes down to cost. On the stack side, copying is cheap. The number 42 is just a few bytes. Making a duplicate is essentially free. It's a single fast memory operation. On the heap side, copying would be expensive. If we had to copy this large string every time we assigned it, we'd be duplicating potentially thousands of bytes. That's slow. That wastes memory. Rust doesn't want to do expensive operations behind your back. If something is going to be costly, Rust wants you to ask for it explicitly. But what if you actually do want to copy heap data? What if you legitimately need two independent strings? Rust gives you a way to do this explicitly. Use the clone method. When you call clone on a string, you're creating a deep copy. All the heap data gets duplicated. You get two completely independent strings. Both variables are valid because they each own their own data. The key word here is explicit. Rust makes you write clone so you're aware that you're doing something potentially expensive. There are no surprises. Here's a rule that ties everything together. A type can implement copy only if it does not implement drop. What does that mean? The drop trait is for types that need cleanup logic, types that have to do something special when they're destroyed, like freeing heap memory. If a type needs cleanup, it can't be copy, because how would you clean up a copy? You can't. It doesn't make sense. So Rust enforces this rule at the type system level. Let's bring it all together. Copy types are copied, not moved. This only happens for simple types that live entirely on the stack. When you need an explicit deep copy of heap data, use the clone method. And remember, types that manage heap resources cannot be copy because they need cleanup logic. Understanding copy types is essential for writing idiomatic Rust. It explains why some operations feel effortless while others require more thought. In our next lesson, we'll explore borrowing. How can we let multiple parts of our code access data without transferring ownership at all? That's the magic of references. See you then.